Hello and welcome. In this video, we're going to take a look at some of the basic rules of exponents and how radicals can be expressed as exponents. And we'll just briefly cover some of the main key points that you need to know. Now let's start off by looking at exponents where the exponent is an integer. So when the exponent is an integer and we have some sort of base a written to the power n, where n is an integer, then this is usually a little bit more of an easier example to try to figure out the meaning of. In this case, that is just a times a times a times a again, and we write out n factors of a all multiplied together. And we refer to a as the base, and we refer to n as the exponent. With that basic definition, then we can come up with 10 essential rules for simplifying and managing exponents. Okay, our first rule might be a more obvious one. A to the power of 1. So that's just like one single factor of a. That equals a. Second rule may not be quite as obvious. A to the power 0 equals 1. Now we'll see why that is maybe after we get past rule number 4. A to the 0 equals 1 is partly a result of some of the other rules for exponents. Rule number 3 is if we have a base a, and we have two factors of that maybe written to different powers, different exponents, then what we can do is we can add them together. A to the m plus n. So you can imagine that we have a whole bunch of a's being multiplied together, and that comprises a to the m. And then we have a whole bunch of a's multiplied together, and that comprises a to the n. Now, if you multiply them together, it's essentially just multiplying as many a's as you have written out, which there would be m factors in the first brackets, and there would be n factors in the second set of brackets, and we can add them together. M plus n factors of a in total. All right, rule number 4 is when we start doing division. Now in the numerator we have a as the base, and in the denominator we have a as the base. If they have the same base, then we can subtract exponents, a to the m minus n. And this is how we learn to sort of cancel out common factors. If we have a times a times a times a, that's a to the 4 on the top. And if I have a times a times a times a times a, and that's a to the 5 on the bottom, then I can start canceling common factors. And this ends up being 1 over a would be the result. And we'll see that this is actually equal to a to the minus 1 if we subtract 4 minus 5. And we'll deal with those negative exponents in a few of these rules coming up as well. Now, what if I had 4 a's on the top and 4 a's on the bottom? If I had a to the 4 on the top, and I have a to the 4 on the bottom, and I start canceling out all of these a's, I don't end up with 0 because you can always imagine a 1 in the front of each of those. And you'll end up canceling all the a's out, but 1 over 1 is equal to 1. Using the same rule, a to the 4 divided by a to the 4 is a to the 4 minus 4, and that's a to the 0. And so that should help you to understand why a to the 0 equals 1. Okay, now it's time to start taking more than one exponent and combining them together in a different way, where we have a base a to the power m, and then we raise that whole thing to the power n. Okay, so now you've got in the brackets here a to the m, and then you're multiplying that whole thing by itself several times. As a result, you'll end up with a to the m times n. And you can try to understand how that works, again, just by writing out a whole bunch of a's, and then taking that in brackets and multiplying it by itself a whole bunch of times. For instance, if you did a squared cubed, you could always write that as a times a instead of a squared. and then you have to cube that. We'll write it out 3 times of the same factor, and in the end, that's the same thing as 6 factors of a. This is an example. Okay, 6th rule. Now, we start getting into how we can distribute exponents. And as you've maybe noticed, all of the rules for exponents so far have to involve properties of multiplication and division. And so that's what you can remember when you're trying to think about whether or not you can distribute an exponent. If you have multiplication, a times b, all to the same exponent n, then you can distribute the exponent, a to the n times b to the n. And same thing with division. A over b, if it's division that you have inside the brackets, you can distribute an exponent on the outside. Now you can try to explain these ones as well as just a couple examples. Let's say as an example, ab cubed is just ab times ab times ab. And because of the commutative property of multiplication, where we can change the order, and due to the association property, the associative property of multiplication, we can actually rewrite this as a times a times a times b times b times b. And we can start thinking about it in that order. And here's how we get a cubed times b cubed. What about negative exponents? I showed you already how if you take a to the 4 divided by a to the 5, you end up with 1 over a. And that should also equal a to the minus 1. Well, in general, if you ever have a written to a negative power, you can always write that as the reciprocal, 1 over a to the positive n. Or because of rule number 7, that's the same thing as 1 over a, all to the power n. Because 1 to the n is 1, and a to the n is what we have in the denominator. Okay, rule number 9 is just applying a couple of the other properties that we already have together. If you have a quotient, a over b, to a negative power, rather than necessarily just distributing the minus n onto the top and bottom into the numerator and denominator, what I can do is apply rule number 8. If I have a negative exponent, I can just take the reciprocal. That gets rid of the negative sign. Or it just simply changes the sign of the exponent. And then if you wish, you can distribute the exponent across the two values in the quotient. And last but not least, rule number 10. Rule number 10, again, kind of uses some of the other properties, but maybe this is a little more convenient depending on the situation if you want to write it out this way. If I have a to a negative exponent, and let's suppose in the denominator I have b also to a negative exponent, then using the properties of reciprocals and simplifying, I could write this as b to the power m over a to the power positive n. So by using a reciprocal, you see how a to the negative n on the numerator is equivalent to a to the positive n in the denominator. And b to a negative power in the denominator is equivalent to b to a positive power in the numerator. Now, what about if the exponents are not integers? What if they are fractions? What if they are some sort of rational number? Then we have to interpret that a little bit differently, although the same properties apply. So let's take a look at those next. Okay, suppose we have a base a and it's raised to some power 1 over n, where n is not equal to 0. Then that is called the nth root of a. What if we have a to a fraction m over n? Well, then we can apply rule number 5 that we just looked at, and we can think about it in one of two ways. We can think about this as being a to the m times 1 over n, in which case this is a to the m, and then all of that to the 1 over n, and we'll get the square root or the nth root of a to the m. Or another way we can think about that is by looking at it as a to the 1 over n times m, because multiplication is commutative. And if we do that, we end up with a to the 1 over n all to the power of m. And we can write that as the nth root of a all raised to the power of m. So there are two different ways we can think about a to the m over n. But we end up with an nth root as well as a power of m. So what is the nth root of something? Well, we call it the principal nth root. Okay, so what is the principal nth root? Well, we say that the principal nth root of a is equal to b, means that b to the power n must equal a. You can think about it like the square root of a is some number where if I take that number and I square it, I get a. Now, in the case of square roots or even powers, we do have one major restriction. We must have a greater than 0 or equal to 0, and b greater than or equal to 0 if n is even. Now, if you think about the nth root as just being the exponent 1 over n, then we can apply some of the same rules for integer exponents from before. So specifically thinking about rules 5, 6, and 7 about how we can distribute exponents across multiplication and division, or how we can combine exponents, we can use those same techniques to distribute and combine roots. So let's look at a few rules that may be a little bit disguised, but they're really the same rules that we just used for integer exponents. The first one, if I take the principal nth root of ab, I can distribute across multiplication. If I take the nth root of a quotient, a divided by b, I can distribute across division. I can also combine exponents together. From integer exponents, a to the n all to the power m is the same thing as a to the n times m. If I were to use that same technique with roots, and I had a root inside of another root, it's essentially like brackets and nested exponents, and I can multiply the two exponents together. So in this case, I can combine that into one single root, and that would be the mnth root. Okay, the fourth root is a little bit more challenging. It's what happens when you take a to the power n, and then you take the nth principal root of it. Now, you would think that hopefully that these two things would just cancel each other out. If I were to cube something and cube root it, it should probably cancel out. If I were to square some number and square root it, it should probably cancel itself out. But that's not always the case. There's two things to consider. A could be a positive number, or a could be a negative number. And it will be a little bit different depending on whether we're taking an even-powered root or an odd-powered root. So let's start off with the odd-powered roots, and we'll look at that as our first case here. If we have an odd-powered root, it does in fact mean that the nth root of a to the n cancels. However, if we have an even-powered root, then it's not exactly a straightforward calculation. We actually have to consider the sign of a. If n is even, then the nth root of a to the n is actually the absolute value of a. Just for a moment, consider what happens if I take -5, I square it, and then I square root that. Now remember, for square roots, you don't have to write the 2 on the edge of the root. It's implied that if you don't have a number on the root, it's a square root. Okay, well, -5 squared by definition is just -5 times -5, which equals 25. And because we have an even-powered root, we're looking for a number that number b, and b squared has to equal 25. But b has to be positive. By definition, this must equal 5. 5 is the number that when I take it and square it, it equals 25. It's the only positive number that does that. Now, unfortunately, we started off with a being -5, and our result is +5, and that's equivalent to the absolute value of a. If I have a odd-powered root and I look at -5 cubed, and then cube root that, then -5 times -5 times -5 is -125, and I'm going to cube root that, and that's okay. For odd-powered roots, we don't need to have a and b positive. We're looking for the only number out there that when I cube it, it equals -125. That equals -5. And in this case, taking a, cubing it, and cube rooting it, I get back a. So it's a little bit different depending on even or odd powered roots. Okay, that gives you some of the basic principles of exponents and roots. We'll look at simplifying them a little bit more in class and use some of these properties to try to make very complicated expressions look a little bit simpler. That's it for now. I'll see you in the next video.